Hello, this is Kent Sanders, Sam Marple, and Robert Rossio, and we are presenting on preventing flow table overflow attacks in software-defined networks. Our group name is Sleep Max Inc. because we like sleep if we can get it, if we haven't played
Lovely. So, in our project, we set out 5 tasks for ourselves. But again, along with that, uh, the theme of risk management, as we talked about in the report, a few of those were optional in case we didn't have time to do them. So the first task was to set up an SDN environment. We used VirtualBox, Mininet, and ONOS controller. Task 2 was to create reconnaissance scripts. So our idea was um, to fingerprint an SDN from the outside based on the time it takes for a packet to return. If it takes unusually long, you can assume that a flow rule has been created. So, um, so you can figure out how the switch designs these flow rules based on return time. So we crafted these scripts to create packets manually, and then we send them. We send in these probe packets. We listen for them and calculate the length of time. Task 3 was to implement this flow table overflow attack. So you send a bunch of these rule creation packets all consecutively, and it can overflow the switch and cause it to slow down like that. Task 4 was to measure the impact of this attack. That, along with task 3, they were both optional, and task 5 was then to introduce a defense against that, to introduce random delays to confound these reconnaissance efforts. Here's some of our work distribution. So we used a bunch of different softwares. We used VirtualBox, Mininet, ONOS, like we mentioned, editors, Emacs, Visual Studio, Ubuntu, Putty. We tried working with like a remote controller. We tried a bunch of different things, and some of them didn't work, some of them didn't. So with the setup of the network, we used Mininet Nonos again. Central switch. Here's our ideal Gantt chart. As you can imagine, a lot of these tasks ended up taking a little bit longer than you'll see on the chart, as tends to happen. Problems pop up, troubleshooting, stuff like that. But we have finished everything we wanted to. Here's a diagram of the attack itself. So here H6 is our attacker. It sends a packet into the switch, which is directed for H1. If there's a flow rule, so there we'll consider in the switch. If there's a flow rule, it will forward to H1 and respond through the switch back to H6 as standard. But if there isn't, then they will go through the controller. There's steps 3 and 4 go up to the controller, come back down from the flow rule, and then direct it as normal. So then when the response gets back to H6, H6 looks at the time, how long it took to respond. If it's a really high response, then we can assume that we can infer that a flow rule was created, and we go compiling and trying to understand which types of packets create rules. Here's some of our pseudocode. We can craft a packet. So we manually crafted all these packets so that we could change a lot of different aspects of them. So we can change from TCP to ICMP. You can change the destination MAC IP import, also the source MAC IP import, protocol type, the flags specifically. So this helps us with, because if you try to just use the TCP command of connect, then it's just always going to start with a SYN packet. You wanted to see what would happen if you could start with a FIN packet or a SYNAC or urgent. So messing with all these flags, we could change a lot of things. The recon again times these responses and keeps track of the ones that take a really long time. And then an attack would be a bunch of consecutive packets all that ended up creating these rules in the recon phase. Here's some of the results that we had. So you can see on the bottom left, after recon, you can find out how many rules are created. There we have So there's 12 rules created, so we can see those packets are the types that will create a delay. If we send all of those together, if we send a bunch of packets similar to that, then we can end up overflowing the rule flow routine. So in all aspects of this project, we focused a lot on these manually crafted packets so that we could find out, so we could really manipulate the packets and analyze what sort of packets were created. A lot of the challenges that we faced had to do with old software, poor documentation, trying to figure out how to manipulate the ONOS controller, the mininet to do exactly what we wanted, even though a lot of people haven't messed with it or it's not very friendly to working with other softwares. And we really took on probably too much work than we should have for just a project that lasts a few weeks. But thankfully, we considered that and made a few of our steps optional. Um, our work could be used. It's got some applications. I mean, our research contributes to future research. We identified it in the report, like policy research that could see if like a specific IP is consistently creating new rules, then you limit the ability of that IP so that you can constrain research. And our code could certainly be used to attack an SDN. That's what I and we accomplished tasks 1, 2, 3, and 5, but again, we skipped 4 because it was optional and we ran out of time. So we took on a bit too much. We were a bit ambitious, but we did complete enough of our work to show results, to demonstrate functionality, and we identified research directions that discussed in our report for future versions of our solution, for better research that SDN could be used in actual use cases. So I'm going to pass it over to Rob.
Yeah, thanks, Sam.
Let
Let me go ahead and get my screen shared up here. All right, can you see that, Sam?
Yeah.
All right. So I'm going to be talking through a quick tutorial. Now, in the interest of time, I'm going to go ahead and kind of skip over some of the nitty gritty details, or at least sort of, just breeze over the setup of the environment. The testing environment that we're working with here is at its core a mini net. It's a single topology, that means single switch, 7 hosts, as you can see here. And it's working off of a open virtual switch with OpenFlow 13 protocol. And there is an ONOS controller installed into the MiniNet virtual machine. So you can see this, the MiniNet is using the local host for the controller, which I've got a terminal over here just to show some of the configurations for the controller that we've set up. Now, these configurations are for this purpose of the testing to make sure that everything kind of simulates the environment that we're looking for. Of course, in this environment, all these hosts are part of the same network, but the concepts that we're going to demonstrate here could be generalized for sniffing outside. Now, the overall idea here is going to be that host 1 is going to be an outward facing service that listens for traffic on a port. It'll be 1099. Host 2 will represent an attacker outside the network who's going to probe to this outward facing service. And this service will call on other services hosted by the other hosts inside the network based upon whatever request the customer or the client outside the network puts forward. So with that, what I'll go ahead and do, I'll pull up some of our terminals here. Basically, the first thing we want to do, we want to go ahead and start running these services. So this is an internal service. It just listens on a port. It's going to be listening for traffic from the host 1, and that's going to be the outward facing port. So I'm going to go ahead and get these started here and send them out of sight. So that's our host 2. We don't want to go to that one just yet. All right, so now that we've got all of our internal services running, I'm gonna go ahead and make those disappear and just pull up these two right here. So what we have here, this is host 1. This is going to be our outward facing service, and this is going to be our reconnaissance. All right, so now we're going to go ahead and run the reconnaissance. And what this is going to do, this is going to send packets. It's going to mutate the payload of the packets and send them into this service. And it's going to measure the latency and see if it can infer when the controller allocates a new flow rule to the table. Okay. So as you can see, went ahead and went through it, and what we got 29 hits this time. Now, what that means essentially is that 29 out of all the packets that it sent, 29 of them had a latency great enough to where it believes, based upon the limits we put into the code, that new rules were created for this. Now, this the decision point for the recon is based statistically, so it would have to be calibrated to the latency of the network itself in order to accurately make a decision there. So that is essentially the way that you might use this reconnaissance to infer what types of packet mutations might cause new rules to be created. And you would use this reconnaissance in order to then launch some sort of denial of service attack, which would attempt to overflow the rule table and cause network degradation or crashes. Now, another capability that we built in here is essentially a random delay into the host. Now, this is intended to kind of simulate what a configuration in the SDN. It would be an SDN app, basically, that would run off Onos, and it would add some random jitter into the rule creation and make this type of reconnaissance much more difficult. So in order to demonstrate that, I'll go ahead and rerun this service down here, and we will actually, let me go ahead and clear that. All right, so now we'll go ahead and run it again. Now you can see there we have 200 new rules created on a network of 7 switches. Clearly, that's not probably what's happening there. So that demonstrates how adding some random delay is obviously going to trip any reconnaissance and make it almost impossible to determine which of those is a real case and which of them is a false one. So that demonstrates our reconnaissance and our kind of study into the problem. And I will turn it back over to you, Sam.
Awesome, that's it. Yeah, so we demonstrated that we can defend against that attack, that we can implement the attack as well, and we hit everything that we set out to do.